Hello everyone, my name is Sashrik Swarnam and this is my official entry for Raman Awards 2025. This is a project, it's a hybrid project between earth sciences and physics. It's a comparative study between the different types of earthquake-proof or resistant buildings. The materials I've used will be displayed on screen somewhere around here. And then, so what I've used are wooden sticks, hot glue, cardboard, clay, a piece of string over here, and then I've used cardboard, marbles, and rubber band exclusively for the simulator. Let's start off by looking at the simulator. As the name suggests, it simulates earthquakes but at a much lower scale. I've made this by using very simple materials, two thick pieces of cardboard sandwiching four marbles, and then rubber bands compressing it so that when I extend it, it returns back to its original position. I've also added two rails so that the marbles don't run away. I've also added the same amount of weight on top of each building, which is 10 grams of clay. This simulates the gravitational and structural pressure that real-life buildings experience. Having the same amount of weight on top of each building makes it a fair experiment. This is the control structure. It's the most basic of the three, and I've only used wooden sticks and glue to build this. This is to show what would happen if we took no measures to prevent this building from collapsing. Next, we have the X-brace structure. In geometry, triangles have been proven to be the most rigid structure, as if you have fixed lengths, the angles cannot be changed. This gives rigidity to structures from high winds and, in this case, earthquakes. On screen are some of the real-life buildings that use this prevention method. Lastly, we have the tuned mass damper, also known as a TMD. It has the same structure as a control, but with a pendulum. It's called a tuned mass damper because we can tune the suspension of this same mass. We can tune it by adjusting the length of the string. This exhibits Newton's third law of motion, which states that every action has an opposite equivalent reaction. When the building sways right, the pendulum sways left, opposing the motion and eventually cancelling it out. When compared to the control, it has a significantly less duration of oscillation. On screen are some of the real-life buildings that use this prevention method. In conclusion, both engineered solutions proved to be significantly more resilient than the control. This goes to show that applied physics principles directly help mitigate earth science hazards. This experiment helps us visualize a few of the many different prevention methods used by architects around the world, especially in earthquake-prone regions such as Japan and the United States, saving millions of lives. Thank you.